Hey guys, welcome back to my channel. In this video, I'm going to be continuing the series where I attempt IB Chemistry HL Paper 1 questions with you guys on camera so that you guys can understand my thought process and attempt these questions yourselves. This will be part 4 in this series, and because of the support I've received over my previous videos, I decided to continue this series moving forward. Before we get started, I'd like to remind you that this channel is quite small, so any help, whether it's a subscription, a like, or a comment, is highly appreciated, and it takes very little of your time, but it makes up so much of mine. So if you guys do enjoy my content and find it helpful, please make sure to support the channel. But without further ado, let's get started with these questions. Question 1 says, what are the units for the rate constant K in the expression K x squared, concentration of reactant x squared, and concentration of reactant y to the power of 1. So if there's nothing there, that's to the power of 1. Well, here we've got to consider that this is overall going to be a third order reaction. Third order reaction. So if it's a third order reaction, we're going to have to remember that for every third, for the final units of the rate equation has to be moles per decimeter per second. So this is actually the final units of the rate constant, not the K. Sorry, final units of the rate itself, not the rate constant. So the final units of the rate would be this. So given that we have a third order reaction, we can already eliminate this option. If we have a third order reaction, well, looking at the molar values, we're going to have the number of moles to the power of 3. And we need our final moles to be to the power of 1, so we'd actually have to subtract 2. So this bit is going to have the units moles to the power of 3. However, we're going to have moles to the power of 1 in our final units for the rate equation. So we're going to have moles to the -2 as part of our rate constant units. So D would be our correct answer. Next question. Consider the equilibrium between nitrogen 2O4 and nitrogen dioxide. Okay, looks like it's a decomposition reaction, which shift the position of the equilibrium to the right. So from here to here. So we have the enthalpy information, we have the number of moles of gases. Well, if we increase the temperature, what will happen? Well, this is a positive value for the enthalpy change, so this is an endothermic reaction. In an endothermic reaction, as the name suggests, we need endo inside, therm, which means basically temperature or heat. So we need to put in heat or temperature. So temperature or heat acts as a reactant essentially. So if we increase the temperature, we're pretty much adding a reactant, and if we add a reactant, we're gonna shift this equilibrium to the right. So this is correct. Decreasing the pressure. If we decrease the pressure, the equation moves to the side with the higher number of gases to almost reset the change in pressure. So if we go from 1 mole of gas to 2 moles of gas, it's going to be a higher number of moles of gas on the right side. So decreasing pressure would actually shift it to the right. So 2 is correct. Adding a catalyst, we know, is a bit tricky. What it does is it increases the rate of reaction by decreasing activation energy, but it does not actually impact the position of equilibrium. So this is incorrect. So 1 and 2 are correct answers. A is the correct answer. Moving on to the next question, we see quite a complicated looking question with a graph. Whenever we see a graph, we're going to know the axes first. I start off with the x-axis. We have temperature on the x-axis. So here's going to be temperature in Kelvin. So here is approximately going to be where we see room temperature, see 0 degrees Celsius. So 100 degrees Celsius would be like here. I like to think about Celsius as well when thinking about Kelvin, because Celsius is used in real life in everyday context, so it helps me understand whereabouts this reaction is going to lie. What type of temperature um, does this translate to in the real world? Sometimes that's useful for paper 1 questions, but in this case it might not be. Let's find out. But first,
I'm going to look at the y-axis as well. We have delta G on the y-axis. Delta G is the change in Gibbs free energy. And we know that when this is negative, so whenever it's this section here, it's going to be a spontaneous reaction. So spontaneous reaction. And in this section where it's positive, it's going to be non-spontaneous. Let's look at the statements. Which statement is correct? The standard entropy change of the reactions is negative. The formula for delta G is really important here. I recommend you memorize it because the formula for delta G is in the data booklet, but this is paper 1, so it's not given. So this suggests to me that paper 1 questions, it's expected that you know that delta G equals delta H minus T delta S. So delta H does not change with temperature, but since we're changing temperature, this whole value changes. So it looks to me that when the temperature increases, right, as the temperature is increasing, the delta G value is slowly becoming more and more negative. So this suggests to me that this delta S value must be positive. We are subtracting this T delta S value, and as the temperature increases, this whole value that we're subtracting would get bigger if delta S is negative. And this actually, the fact that this whole value gets bigger is suggestive in the fact that we see delta G becoming smaller and smaller, becoming more and more negative as delta T increases. The standard entropy change of the reaction would be positive. So statement 1 is incorrect. The standard enthalpy change of the reaction, well, we see that at this temperature, at around this temperature, it's positive. So delta H must be positive as well because at lower temperatures, delta S is going to be more and more smaller. It's going to be smaller and smaller. And if we're minusing a smaller number, well, this thing is going to be this delta G value is going to be more dependent on the delta H value. This stuff about delta G and delta H is really confusing to explain in a short question, but if you guys did follow, if you guys are using this video for revision, you guys should be able to follow. And so delta H being positive is a possibility. So let's just check the other options. At higher temperatures, the reaction becomes less spontaneous. That's not true because we get it more negative at higher temperatures, which means it's more spontaneous. The standard enthalpy change of the reaction is negative. That's not true because like I said earlier, at low temperatures, this value is going to be super low. So the delta G value is going to be dependent on the delta H value. And we see here that the delta G value is eventually, or at some point in low temperatures, it's positive. So that means when delta G is more dependent on this value, it's more positive. So this value must be positive as well. So B is the correct answer. Which species produced by successive dissociations of phosphoric acid are amphiprotic? Amphiprotic means that a substance can act as a acid or a base, more specifically a Bronson-Lowry and an Arrhenius acid or base. So we've got to think about ones that have a H and have a H and also a negative charge essentially, because a negative charge indicates to me in this circumstance that it can gain another H plus and act as a Bronson-Lowry base, while the presence of a H suggests to me that they can act as a Bronson-Lowry acid and get rid of that H. So I'm going to look for the options that have two H's. Oh, sorry, a H and a minus charge, which is going to be option B, which is going to be the correct answer for this question. What is the pH of this molar sodium hydroxide? Okay, so for these questions, it's a bit tricky. We're going to write out the equilibrium expression. So the Kw for water is this, and actually, no, we don't have to. That's a paper 2 question. This is paper 1, so we don't have to. We just need to remember that sodium hydroxide is a super strong, the strong base. So what happens is it fully dissociates. Full dissociation means that we can assume that the concentration of sodium hydroxide is equal to the OH minus concentration. So the concentration of sodium hydroxide is equal to the OH minus concentration. And if we have a pH of if we have a concentration of this much sodium hydroxide, that's going to be sodium hydroxide. We're going to have, this is that in non-scientific notation, um, this is going to be the concentration of OH minus. So if we do POH, we're going to get 3, POH of 3. If we have a POH of 3, we can work out pH by doing 14, or pKw, sorry, equals pKw minus POH. Here, pKw is going to be P of 1.0 times 10 to the negative 14, which is just going to be 14, minus POH, which is 3. We're going to get 11 as our answer. Which species acts as a Lewis and Bronsted-Lowry base? A Lewis base can donate an electron pair, and a Bronsted-Lowry base accepts a proton. So we're going to think about something that can both accept a proton and have a lone pair of electrons to donate. So if we look at NH4+, we know that this actually does not have any lone pairs of electrons, so we can eliminate this. Same with BF3. You're going to remember that boron is an exception to the octet rule, and in turn it's going to have a satisfied octet with 6 outer electrons, and it won't have any lone pairs. Similarly, Al 3+, so the Al ion in this case is 3+, the central metal ion. It's going to have a complete octet, and it won't have any spare electrons pairs. However, OH minus, if we draw it out, it looks something like this. So first, actually, let's go through the steps of drawing it out. We first find out the number of valence electrons: 6 for oxygen, plus 1 for hydrogen, plus 1 for the negative charge. We have 8 electrons. Next, we form an OH bond, and then we have 2 electrons for the H, and then we need 6 more electrons for oxygen, which we have right here. We notice that this has a minus charge, so it can act as a Bronsted-Lowry base and accept a H plus ion or proton and form H2O water. And it also has lone pairs of electrons to donate to another substance and act as a Lewis base. So OH minus is definitely the right answer. A buffer is produced by mixing 20 cubic centimeters of 0.1 molar ethanoic acid with 0.1 molar sodium hydroxide. What is the volume of sodium hydroxide required and pH of the buffer? Well, if we're trying to make a buffer, we need to mix a weak substance with a strong opposite substance. So if we have a weak acid, we're going to mix it with a strong base. If we have a weak base, we need a strong acid. So here we can see, we know that, you may not know that ethanoic acid is a weak acid, but the fact that sodium hydroxide is mixed with it, and sodium hydroxide we all know is a strong base, it should be an indicator that this ethanoic acid is a weak acid. So if we have a weak acid, when we're making a buffer, we have to neutralize it with, we should partially neutralize it with a strong acid. So partial neutralization is important in the creation of a buffer. So if we're going to partially neutralize it and they're the same mole, we're going to have less volume of sodium hydroxide than the volume of ethanoic acid. So we can eliminate options A and B. Next, we're going to consider what type of buffer we're trying to make. Whenever we try to make an acidic buffer, we have a weak acid and a strong base. So here, since we have a weak acid and a strong base, we can assume that this is an acidic buffer. And so we can pick a pH that's going to be more acidic, which is going to be lower than 7. pH lower than 7. So we can eliminate these two options. So based on the options we have remaining, D seems to be the correct answer. Which change represents oxidation? Oxidation is the loss of electrons, and it represents the oxidation state going up. So let's see. These are all neutral molecules right here. So I'm thinking of chlorine as being the thing that's going to be oxidized, for potentially oxidized, because H and O, so hydrogen and oxygen, typically have +1 and -2 charge respectively. So let's find the charges in this molecule. So we have -2, and overall charge will be -8 for oxygen, for the 4 oxygens, and +1 for the hydrogen. And the overall molecule is neutral, so +7 for the chlorine, because all the charges, when you get them together, they add up to 0. Here we have +1 for hydrogen, -6 for oxygen, because -2 times 3. So the overall, the charge for the chlorine must be +5. So we have the charge of chlorine going from +7 to +5. That's a reduction in the oxidation state. So it is also going to be reduction. So whenever the oxidation state reduces, it signifies gain of electrons, and that's reduction. So it's not oxidation. Here we have nitrogen. So nitrogen has an oxidation state of 0 when it's in its diatomic form. Here we have +3 for the hydrogens, and we're going to have -3 for the nitrogen. And so this is again reduction, so we can eliminate that option. Here we're going to have +1 for each nitrogen and the -2 for oxygen. Then we're going to have +2 and -2 for the nitrogen monoxide. And here we see an increase in oxidation state, which is going to be oxidation. So C seems to be the correct answer. A reaction takes place when a rechargeable battery is used. So we have lead dioxide, we have 4 protons, 2 sulfate ions, and we have 2 lead sulfate and water. So H plus is reduced. Let's see. So we have H plus going from H plus. That's going to be the oxidation state as well, even though it's an ion essentially. And we have the a water molecule that's neutral overall. We have -2 charge for oxygen and 2 H2Os. H2s, sorry, should be +2 charge. So +1 times 2 to get an overall neutral molecule. So it is in fact not reduced because the charges stayed the same. The oxidation state of metal Pb changes from O to +2. Well, metal here is going to be O. Here it will be +2, but here we have lead dioxide, which is going to be um, um, it's going to be -2 times 2 charge for the oxygen. So each oxygen is -2, and since we have 2 of them, we're going to have an overall -4 charge or oxidation state for the oxygens, and we're going to have a +4 for the lead. So to make the overall molecule neutral, so lead is +4. However, I think because it's referring to the Pb metal, we're only looking at this one. Yeah, that would make more sense. So this is an unnecessary step. So lead in its solid state, when it's a neutral molecule, it must have an oxidation state of 0. And here sulfate ion we know has a charge of -2. So lead, since we have one lead per sulfate ion for a neutral molecule, lead here lead must have a +2 charge. So it is this statement is correct. Lead O2 is the oxidizing agent. Well, this one's a bit tricky, but I noticed that for each of these options, there are at least 2 that are correct. So, because the first option is incorrect, we can eliminate all of these options, and C would be our only answer. Lead 2 is going to be the oxidizing agent because we have lead that's going to be +4, that's reduced to +2. So, because this substance is reduced, we can determine that this is the oxidizing agent, because the oxidizing agent is the species that's reduced and the reducing agent is the species that's oxidized. So C is our correct answer. Which statement is correct for the overall reaction in a voltaic cell? So we have silver nitrate plus nickel solid to form 2 silver solid, and we have nickel nitrate aqueous. Electrons flow from the silver electrode to the nickel electrode. In this case, we're going to see the oxidation states first. So we have 0 for nickel and +2 at this stage. So if you guys aren't following the oxidation states, I recommend you guys learn a bit more about oxidation states, and please comment down below if you would like to see me make a video on it. I would be happy to do so, but I'm going to go a bit faster because at this rate, I assume you guys know how to work out oxidation states. Silver is going to be +1 because the nitrate ions are all going to be -1. It's going to be -1 times 2. So we have silver going from +1 to 0, so silver is going to be reduced. So reduction occurs at the cathode. So silver is going to be at the cathode. So if silver is at the cathode, it's not going to have electrons flowing from it to nickel. It's going to be from nickel to the silver electrode. So this is in fact incorrect. Nickel is going to be from 0 to Ni2+, that's correct. At the cathode, the negative electrode, that's not true. In a voltaic cell, the cathode is the positive electrode, and oxidation never happens at the cathode. reduction happens at the cathode and oxidation happens in the anode. In fact, because nickel is oxidized, this happens at the anode. So nickel is going to be oxidized. Ag plus is reduced to Ag at the anode. That's not true, because at the anode you have oxidation. Ag has more positive standard electrode potential value than nickel. So the standard electrode potential value is used to determine which species will be oxidized and which will be reduced. We know that the species that's reduced will have the higher value, and the species that's oxidized will have the lower value or even negative value. So since we know that Ag in this reaction is going to be reduced, we can determine that it has a more positive standard electrode potential or a higher standard electrode potential than nickel. So D is the correct answer. We could have gotten that by the process of elimination, but that explanation at the end was for you guys to understand how else you would determine this question and why this right answer is the right answer. In the electrolysis of aqueous potassium nitrate using inert electrodes, 0.1 moles of gas was formed at the cathode, negative electrode, which is correct. So if we're thinking about the cathode, again, cathode, we have reduction happening at the cathode. We're going to think about the reduction potentials. So at the cathode, we're going to have cations. The only cations in this aqueous solution will be the K plus ion and the H plus ion. The K plus ion is a really strong reducing agent, and it has a high tendency to be oxidized because this is metal. Metals have a higher tendency to be oxidized than hydrogen. So K plus, since it's also at the top of the reactivity series, is going to be unlikely to be reduced. So it's going to be less likely than hydrogen to actually be formed at the cathode. So hydrogen is the right answer. And hydrogen is definitely going to be produced at the cathode. And I just realized that that was a waste of time because we're actually looking at the anode. So, um, yeah, that's a bit weird. So if we have 0.1 moles of gas formed at the cathode, that's going to be H plus gas. Next, we're going to think about nitrate. Since H plus forms at the cathode and the anode will have oxygen, we can eliminate the H plus options. And we'll look at the charges. Let's compare the charges of H plus with oxygen. So H plus is a +1 charge, whereas oxygen is a -2 charge or 2 minus charge, right? So if we took the absolute value of the charges, just take the value. This is a 1 charge and this is a 2 charge. That's how big the magnitude of the charge is. So if we have electrons moving into this to be sorry about that, my friend just texted me on Discord. We're going to think about the charges. So we have a +1 charge and a 2 minus charge. So the ratio of the charges is going to be 1:2. So for each 1 electron that's going to be going into this, that's going to be reducing H plus, we're going to have 2 electrons being removed from oxygen. Right? Oxygen is going to have 2 electrons removed from it. So because its charge is bigger, it's going to have it 2 times bigger. The easy way to think of it is it's going to require 2 times as much electrons or 2 times as much electrical charge to be removed from it than hydrogen gains electrons. So it's really confusing at first, but let's think about it this way. So if we have 4 electrons removed from, oops, I didn't mean to zoom in like that. If we have 4 electrons removed from 2 oxygens, how many hydrogens can we form from it? Well, we can form 4 hydrogens, right? Because we have 4 electrons that can attach to um, 4 hydrogens, 4H plus ions, so we can have 4H atoms, right? And hydrogen is diatomic, so we're going to make 2 diatomic molecules. Now for the oxygens, we had 2 oxygens, right? 2 times oxygen. So 2 times oxygen, we get 1 diatomic molecule. So we've had 2 hydrogen gas molecules, for each 1 oxygen molecule. So we're going to have a 1:2 ratio. And the 2 ratio here is going to be 0.1 moles of H plus hydrogen gas. So the 1 ratio, or the oxygen gas ratio, is going to be half of 0.1, which is going to be 0.05. So it seems to me that this is the correct answer. So this is kind of hard to explain because the ratios are to do with um, electrolysis, and it's more circuits in sequence topic in chemistry. So I'd much rather prefer to explain this fully in a future topic. So if you guys do want to learn more about this and not have a sort of a weak explanation like the one I did just now, please leave a comment down below. I will make a better video on it that's more in depth and will probably facilitate stronger understanding. But I assume you guys who are on track to revise for your final exams um, are able to understand that topic understand my explanation quite well. But if you're a beginner, it'll be a bit difficult. What are the functional groups in the aspirin molecule? Okay, so in the aspirin molecule, we have a aldehyde group here, we have a hydroxyl group here, we have another aldehyde group, we have I believe this is a ester group, we have a phenyl group as well. So ether, I don't think there's an ether group. There is an ester group. I think this is an ether because we have wait a minute. Yeah, we have an O, and then we have an O double bond to the carbon. So this is gonna be this junction with the oxygen is present in both esters and ethers, but I think this is an ester because of this aldehyde group here right next to it. So again, we have the carboxyl group as well, not the ether group, but we have the carboxyl group right here. Carboxyl group is for carboxylic acids. So 2 and 3 seem to be the correct answers, so C is the correct answer. Which molecule has a tertiary nitrogen? So tertiary nitrogen is going to have 3 carbon molecules attached to it. So let's see, which of these could it be? It seems to me from just inspection, I believe it is this molecule right here. You don't have to draw out the structures, but if you guys are familiar with the bracket notation, you guys should be able to determine which one is which. So you can I don't recommend drawing out each structure, especially because this is question 33 and you're nearing towards the end of the exam and you're unlikely to have ample time to draw out every structure. But actually, I take that back. Since it is paper one, even though it is HL, most of you guys with enough practice should be able to have spare time to check your answers. So I do recommend checking your answers by drawing it out, but you don't have to draw it out for this example. But I will draw this out and show you why this is the case. So it will be like this. So becoming more comfortable with drawing out organic molecules and getting more comfortable with topic 10 is going to be really important for most of your chemistry exams, um, paper 1, paper 2, etc. So here I've drawn the bracket notation. So the bracket notation just means that the previous molecule, we're attaching whatever this is onto it. So here this would mean that we're attaching uh, we're we're having one of these groups and we're attaching 3 more of it onto that. Here we're attaching two of these um, methyl groups to this nitrogen. But since we have 2 methyl groups, it's not going to be tertiary, it's going to be secondary nitrogen. Here we have this C3H7 group attached to the nitrogen on one side and also 2 methyl groups attached to the nitrogen on the other side. So that's going to be a total of 3 carbon atoms attached to nitrogen. So we're going to have a tertiary nitrogen. What can be determined about a molecule from the number of signals in its H-NMR spectrum? From the H-NMR spectrum, the number of signals determines the number of hydrogen environments. This is just a recall question. What is the major product of the reaction between 2-methylbutene and hydrogen bromide? 2-methylbutene, hydrogen bromide. Hydrogen bromide is a halogenoalkane. So for this question, I would recommend drawing out 2-methylbutene. So since it's but, we can draw out 4 carbons like that. And 2-methyl, we can attach the methyl group here. 2-methyl, 2-butene, 2 is going to be there. Sorry, no, that's 1. So this is 2 is going to be there. So let's draw out the hydrogens as well. It's good in IB to learn to draw out the hydrogens because you won't get marks in IB if you don't draw out the hydrogens. You can't leave empty carbons. And if we have hydrogen bromide, we're going to be attacking this double bond, so the H is going to become more partially positive, and this one's going to be partially negative, and this one's going to have homolytic fission, and this H plus is basically going to attack this one. And remember, we're going to have, according to Markov-Nikolson's law, this H plus is going to attach to the carbon with the most number of H pluses. So in this double bond, we're going to attach to the carbon, whichever one has more bonds to hydrogen. So this carbon right here, we'll call carbon number 1. Make this one carbon 2. Carbon 1 will be... Actually, no, we should probably consider... I know I make contradictions sometimes, but it's because I feel like this method is better for the explanation than the previous one I was about to use. So that's why. So let's label these carbons 1, 2, 3, and 4. So carbon 2 has no bonds to any hydrogen, so this one has 0 bonds to hydrogen. Carbon 3 has 1 bond, so we're going to have the H bonded to here, and the double bonds eliminated. And by default, the Br is going to be here. So our new molecule is going to be 2-bromo, 2-bromo, 2-methyl butane. So D is the correct answer. What is the product of the reduction of 2-methyl butanal? 2-methyl butanal, but is going to be like that. 2-methyl butanal aldehyde, so it would be at the end, so it's going to be like that. It'll be like that. So if we reduce an aldehyde, we're going to get a carboxylic acid, I believe. Wait, no, reducing an aldehyde, never mind. So that's oxidizing an aldehyde. I recalled that wrong. So the rule is, if you have a primary alcohol, you oxidize that, you get an aldehyde, right? And then if you oxidize that further, you get a carboxylic acid. So if you reduce, which is the opposite of oxidation for an aldehyde, we go backwards. So we're going to have a primary alcohol. So if we can eliminate these options, then we can draw out the other two alcohols. It's going to be like this. Butane 1-ol. That seems to be the correct answer, because the first option is indeed a primary alcohol. So A is the correct answer. Which molecule is chiral? Chiral means that we have a carbon molecule with 4 completely different groups attached to it. So let's try chlorobutane 1, 2, 3, 4. 2 chlorobutane. Well, we're gonna have 1 chloro group, 1 H group, 1 carbon group, and 1 2 carbon group. So this indeed seems to be a chiral molecule. So A seems to be the correct answer. The molar mass of a gas determined experimentally is 32 grams. Its literature molar mass is 40 grams. What is the percentage error? Percentage error is going to be the actual minus literature over the literature. So it's going to be 0. So minus 8 divided by 40, which is going to be that. And then we're going to multiply that by 100 because it's a percentage. That's going to be 20% or negative 20%. In this case, we can just pick C because the absolute value is what matters. What is the density in grams per cubic decimeter of a 34-gram sample with a volume of that? Well, in grams per cubic decimeter, we just got to divide the number of grams by this number. So we have 34.79 divided by 12.5. So that's going to be about, that's going to be bigger than 1, so we can eliminate these options. And for these answers seem to be the same, but we've got to think about the number of sig figs. Since we're doing a division calculation, the total number of significant figures in the final answer will be equal to the value with the lowest number of significant figures in the calculation. So 3 sig figs is the lowest. This one has 4, this one has 3. So I'm going to go with the one with 3 sig figs, which is going to be D. Which technique is used to determine the bond lengths and bond angles of a molecule? Infrared spectroscopy does not work with bond angles. Mass spectroscopy again. HNMR, no. Crystallography is indeed the correct answer. Now it's time to have a look at the answers and see how we went. Okay, so it looks like we managed to do well and we scored 20 out of 20 for the 20 questions that we attempted. So that's a super high score and job well done on you guys' part and my part. So we seem to have gotten solid understanding of all these paper one questions, but again, this paper one could have been a decently easy paper one. Honestly, looking at the questions, I believe that this paper one was a bit easier than the other paper ones. Less there were less uh, basically the distractors weren't as difficult as with other paper one questions that I've encountered before. So other than that, guys, it's going to be the end of the video, and if you guys did enjoy this video, don't forget to support the channel. It means so much to me. Please leave a like, subscribe, and comment down below any video recommendations you have and any feedback you have from this video. There's always something to learn. And if you guys did find this video helpful, please don't forget to check out my other videos on the channel. This is part 4 of this series where I attempt paper 1 questions. So check out parts 1, 2, and 3 so that you guys can do more paper 1 questions with me in preparation for your IB Chemistry HL exam. Other than that, guys, see you in a future video. Peace out.